This lecture is going to show you how to run K-means clustering in R. So let's start out with the newspaper example that was discussed in the book, and I've used it in class examples as well. So that data set is, I've already read it in. You can get it off Blackboard if you want to click along. The name of that data set is NP2. So let's do a quick summary on NP2. And what you're going to see is that it has two columns, time and sections. We can find the dimension of this, and so it has about 2,900 rows with these two columns. Now, to fit a K-means clustering model to these two variables, what we need to use is the Kmeans function. So we can get some help on that. If you type $K-means, you get help on it. It's really a pretty simple function. There aren't that many options. So if we look at what we have to do here, x is going to be the number of will contain the data that you want to cluster. So pass to it any data that you want to have clustered. Centers. Centers, you'll usually pass the number of clusters that you want. So if we want a 5-cluster solution, we'll have centers equal to 5. You can set the maximum number of iterations, and you can also play with the number of starting values. So remember I said in class that K-means is not guaranteed to converge to the optimal solution. So the safe thing to do is to run it with a lot of different starting values and let R pick the best one. Okay, so I think we're about ready to run one. So let's go do that. You always want to assign the result of a K-means clustering model to some object. So I like to call it fit. This is my fitted object. So we're going to pass K-means. And now the first argument, you'll notice that we're getting some help at the bottom of the page here, is the data set we wish to analyze. So I could just type NP2. That will work fine in this case. However, sometimes you don't want to use all of the columns in a data set. You only want to use certain columns in the clustering. If that is the case, then you have to specify those columns, and you do that with these brackets. So I'm going to put comma, so that means the fact that I don't have a first entry, so there's nothing before the comma means give me all the rows. Now, after the comma, I specify which columns I want. So one way to specify that would be 1:2. So this means count from 1 to 2. In other words, use both columns 1 and 2. And that's one way to do it. A third way that sometimes you'll have to use is you can specify a vector of values. So if I said C 1, 2, what that means is use, again, columns 1 through 2. The reason you want to use this vector notation, the C business, is sometimes you want to omit some column in the middle. So let's say I have 5 columns and I want to use columns 1, 3, and 5. Well, if I said C 1, 3, 5, then that would pick those 3 columns and omit columns 2 and 4. Right. None of this is really necessary in this case because the data set is is already set up where I'm going to use all the columns. So this makes my life very easy. So we're going to have 5 different clusters. So that's what that center means. And then I'm going to set max iter to 100, and let's set n start equal to 100. So this is going to take, oops, did I misspell that? Iter max is instead of max iter. So let's go change this to iter.max. And it takes less than a second to run. Now, I've got this object fit. Let's go take a look at what's in fit, and we'll do that with a names command. So you'll see that fit really has 4 components. It has cluster centers within sum of squares and the size. Now if you want to know what these are, go back to the help page, and if you go down a little bit, on every help page you have this value section that describes the fitted value. So cluster just tells you to which cluster each observation is assigned. Centers gives you the cluster means. Within sum of squares tells you the sum of squared distances between each observation assigned to a cluster and the cluster centroid. and size gives the number of points in each cluster. So let's go take a look at fit $size. So what we can conclude is that there were 670 observations assigned to cluster 1, 509 to cluster 2, and so forth. Now let's take a look at fit$cluster. Actually, before we do that, let me show you the length of fit$cluster. It's a pretty big object. It has exactly the same number of rows as the original data. So 2,939 observations. For that reason, I don't want to print the whole thing. You especially don't want to print it if you have 100,000 cases that you're clustering. Otherwise, you'll fill up your screen with a bunch of numbers that you don't really care about. So if I just print the first 10 observations, what this is saying is that the first 10 observations were all assigned to cluster 2. If I run a table on this, so let's do a table fit$cluster, you'll see that you get exactly the same thing as you got for fit$size. So notice there are 670 ones, and that's the size of cluster 1. There are 509 twos, and that was the size of cluster 2, and so forth. So they really didn't need to give us this size component of the fit object. We could have just gotten it with table. All right, so that's what the centers does. Let's now look at the cluster component. Let's look at centers now. So fit$centers is going to be fit$centers gives us a k by p matrix. So k is the number of clusters, p is going to be the number of variables that you've clustered. These are the cluster means for each of them. Now we could plot this. So let's go plot this. And what you'll see is we get the 5 clusters that we discussed in class. Down in the lower left is your non-reader, here are your light readers, your skimmers, your heavies, and your selectives. Now, if you want to make this graph a little bit nicer, you could do something like this. You could say color equals 1 through 5, and that would assign a different color to each of these cluster centers. So whatever color number 1 is, I think that's the black, and so forth. All right, so you could do all those sorts of things. If you want the original scatter plot, so let's do a plot of the original data. So the original data was NP2. Now I could just do plot NP2, and that's fine. I'm going to actually add some arguments to this. So let's put time on the x-axis and NP2 sections on the y-axis, and you get exactly the same thing. There's actually a lot of values on each one of these dots. So there were 370 zeros. So that point is being plotted 370 times. We can add a little bit of random noise to this. So if I do jitter, jitter adds a little bit of random noise to each of these observations, and then that'll kind of spread them out, and we can see how many values are actually there. So I'll jitter both of these. And so now you can see that really you only have one of those, was that 3, 0, where you have a whole bunch of these. And you can start to see where these clusters came about. Now we can superimpose the cluster centers with the points command. So let's do fit$centers. And let's, I'm going to make the plot character, let's do it as number 3. I think that's a plus sign. And we're going to make it bigger. So character expansion equal to something big like 3. All right, and so you can see that here are those cluster centers superimposed on this. All right, we could make this even better if you want. Let's go back to the original plot, and I'm going to say color is equal to, now let's go back to the clusters. So that would be fit$cluster. And you can see that, okay, all the observations assigned to this non-reader segment will be coded in red. And then, here's all your skimmers. All of those get assigned to the skimmer segment and so forth. And then we can go back to the points and add those. All right, so those are just some ways of playing with the fitted objects. All right, the only other thing that you want to look at is this fit dollar within sum of squares. And this gives the sum of squared distances between the observations and the cluster centroids. We can turn these within cluster distances into variances simply by dividing by the number of cases in each cluster. So fit dollar size times the number of variables that we've had. So we've got two variables in this that are contributing to those distances. So here are your variances. Those can also be turned into standard deviations just by taking the square root. So it's a little bit more intuitive to think in terms of unsquared units with standard deviations than it is with squared units. And so what you'll see is that within cluster variance for cluster 2, that was that red one down there, is much lower than the others, which are all kind of up in the 0.8, 0.9, 1 area. So that's going to tell you roughly what the typical deviation is of any observation assigned to that cluster. So it was the typical deviation from the center. That's the basics. And now I've made some functions that will display this fitted object in a better way. Now you have to do this once, only once, and then you can use these functions forever. So these functions are located in a file that I put on Blackboard called Kmeans. Now on my computer I put them in a certain folder. You have to read these functions in and you have to do it once. So source reads in a bunch of code. These functions happen to be in users, ECM, teach, lectures, and the file was called kmeans.r. Again, you only have to do this once. This reads in two functions that will display Kmeans objects in a much nicer way. You need to do one other thing. You need to install a package. So go up to Packages and Data, and Package Installer. So you want to get the entire list, and then you want to download a package called Lattice, Lattice, and that'll come up. You just click on the package, and then you click on Install Selected. Now I've already installed it, so I'm going to get a little error message, but when you do this, you won't get that error message. Okay, so we've just installed that package. Again, you only have to do this once. Now, between the source command and then this installing Lattice, you now have two additional functions that'll make reading these things a whole lot easier. So, for example, there's a summary function, and we can apply that to any fitted object, and you get more useful information than the default summary function in R. So, in particular, you have one row for every cluster that you've taken. Here are the cluster sizes. The next column gives you the percentages. Here are the means. Then you have those within cluster standard deviations displayed as RMSE. You also have a few additional statistics that we've talked about in class that evaluate the quality of the fit of the cluster solution. All right, so let's go to the theater example now briefly. And so the theater example has quite a few variables in it. So we want to cluster on the first 5, and we'll use the remaining ones for profiling. So to do this, the first thing we should do is probably standardize the variables. So let's make a new object called theater, ztheater, which will be these standardized values. And you standardize with a function called scale. And so I'm going to use theater. We only care about the first 5 columns. So we're going to cluster on attitude, planning, parents, good value, and get to. And so that's going to specify just those. Now, if we do a var var finds the variance of z theater, and you'll see that the variances, so that those are the things on the diagonal, are all 1. And so that's because we've standardized them. So every column now has variance 1. So let's create a fitted object. Fit will be Kmeans, and we'll put z theater, spell it right, and we'll take 3 clusters, iter.max equals 100, and let's have n start equal to 100 as well. And that took less than a second. Now let's do a summary on fit, and so you can see how large each of the clusters are. When you've standardized the data as I have here, the mean is 0, and when you have a mean of 0, any positive values indicate above average, any negative values indicate below average. So you'll see that cluster 2 is kind of above average on everything, cluster 1 is below average on everything, and cluster 3 is mixed. Now I have a plot function that was also, you just sourced in with that kmeans.r. So if we do a plot of fit, you're going to get a graph that I think is very readable. So it plots these cluster means. So let's go back to what we got with the summary function. I said that cluster 2 is above average on everything. That's clearly shown in this graph. So you can see that here's cluster 2. You have one panel for each cluster, and sure enough, cluster 2 is very positive about on all aspects of theater. The planning dimension, they're kind of in between. They're just barely above average, but that shows up very nicely in this graph. If we go back to the means, cluster 1 was negative on everything, and that shows up here. And then cluster 3 was kind of mixed. They don't have very high perceived value. They're below average in terms of getting to the theater, but they have a good attitude. Their parents did it, and they're quite high on planning. So I think this is a very good graph for making sense of a lot of different cluster solutions, and you'll, when you do a practical use of clustering, you'll be running many solutions. Okay, that's it for this